So in this video I want to talk about the notion of a reaction rate. So this really brings together all the work we've done before in the last three videos that discussed stoichiometric amounts, stoichiometric coefficients, and rates of change. So remember that when we talked about the rate of change, it was noted that the rate of change, the actual value of the rate of change, depends on which species you actually measure. So for example, rate of change of B is that, rate of change of A is that. And we noted that if the reaction is going left or right, then the rate of change of B was positive and the rate of change of A was negative. Okay, so they're slightly different. And it was even worse if the stoichiometric amounts were slightly different. So if you had dimerization, for example, and again I can write down rate of change of B and the rate of change of A. The question is now, what's the relationship between these two? Well, because of the stoichiometric amount, it turns out that dA by dt equals minus 2 dB by dt. The reason for that is because for every B that appears, two A's disappear. So that means that A disappears twice as fast as B, and that's why we have that 2 there. The negative sign is just to take into account the fact that A is made and B is made and A is consumed. So what's this got to do with reaction rates? Well, wouldn't it be nice if we had some way, some general way of indicating how fast the reaction is going, irrespective of which species we use to measure the reaction rate. So that means I could quote a reaction rate without the person worrying about, well, what species did you use to measure that reaction rate? Now, I'm going to do something that looks a little bit arbitrary at the moment, but bear with me for the time being. Let me take this equation here and divide both sides by minus 2, and I'll get something that looks like this. So all I've done here is divide both sides by minus 2, and I'm going to define this to be the reaction rate. Right, we're V. So we usually indicate the reaction rate with the symbol V. So this may seem a bit arbitrary, but it isn't really, because if you look closely, what have we got here? Well, this here is actually the stoichiometric coefficient for A, and this is the stoichiometric coefficient for B. So what I've gone and done is I've gone and taken the species, the rate of change of the species, and divided it by its stoichiometric coefficient, and I will then define this as the reaction rate V. So this is a very important equation. This basically standardizes the way in which we can express reaction rates, and it's irrespective of which X I use. So for example, if X is a reactant, this will be negative, but so will this be negative, so the whole thing is positive, so the reaction is positive. If X were a product, well, so will Cx be positive as well, and dx dt will be positive, and so the rate of reaction will be positive again. Now I can rearrange that equation in a slightly different way, so that I can write down, I don't want red, let's have another color. I can write down dx by dt equals cxv, and this now expresses the rate of change. Basically this is a differential equation. It expresses the rate of change of x in terms of the reaction rate and the stoichiometric coefficient. So let's consider an example. Let's say I have A goes to B. Right, well, the stoichiometric coefficient for A is minus 1. Stoichiometric coefficient for B is 1. And I can write down now the rate of change of A is minus 1 times V, and the rate of change of B is plus 1 times the reaction rate. Now this system then forms a system of differential equations which I can solve, and this is basically a model for this simple system here. And the next video we'll consider how this affects networks of reactions.